Hello, we're from the Dr. McMahon lab, quantum computing error mitigation. I'm Arhan Reddy.
Satvik Ranavali.
My name is Vihan Krishnakumar.
So as for abstract, quantum computing has the power to significantly speed computations compared to classical computers. However, as like Dr. McMahon said, error these computers are really prone to errors due to outside interactions, which causes the data to be noisy. So we're currently finding a way to decrease these errors and make quantum computers more stable. And to simulate realistic errors, we're using surface codes, which we're actually implementing using the Q surface Python module. So in order to actually decode these surface code errors, we're using convolutional neural networks for feature extracting, which are the patterns we're looking for in those codes, and the graph neural networks to kind of analyze the graph that the surface code is to actually correct those errors. And by training and evaluating both parts of our solution, we can drastically increase performance in quantum computing and make it significantly more practical, which will allow for major developments in the field of quantum computing.
So what is quantum computing? Quantum computing is a section of computing that combines quantum mechanics with classical computing, employing phenomena such as superposition. If classical computing is like flipping a coin, quantum computing is allowing that coin to exist between the states of just heads and tails, revealing almost infinite possibilities. A common example is Schrodinger's cat, where you don't know whether the cat is dead or alive until you open the box. In quantum computing, we deal with quantum bits, also called qubits. Unlike classical computing, which is consisted of zeros and ones, quantum computing uses bits in superposition between the states of 0 and 1. Zeros and ones are represented by two-dimensional standard unit vectors, and a qubit can be defined as a unit vector in the form of A times the 0 qubit plus B times the 1 qubit.
So what is error? So quantum computers are powerful yet fragile, and qubits are easily disturbed by noise in their environment, which can cause error. In quantum computing, there are two types of errors. Bit flip error, where the 0 and 1 components are switched, and phase flip error, where one of the components is multiplied by -1, represented by a matrix C. All other types of errors can be seen as a combination of these two. And because these errors change the information stored in the qubits, they can cause data corruption and can result in incorrect information being stored. Currently, currently error technology only lets about roughly 1 in 1,000 errors, but an error rate of 1 in a million is needed for large-scale practical quantum computing, according to researchers. So quantum computer and surface codes. Unfortunately, quantum computers, although powerful, have a downside, and they're often affected by quantum error, which is often caused by environmental disturbances such as thermal vibrations. To protect our qubits from being affected by these errors, we utilize a structure called the surface code. Surface code makes it harder for qubits to spread out, which allows quantum computers to save qubit information across multiple qubits, thus making errors easy to correct. In the picture to the left, you can see an image. So the small circles are the data qubits, and they're the ones that are actually holding that information, while the squares around them are called stabilizers, which constantly check for errors. Squares marked with X are checking for bit flip errors, and the squares marked with Z are checking for phase flip errors. And each qubit is checked by both of X of the X stabilizer and the Z stabilizer. And that's why there's semicircles in some places to account for the fact that some of the boundary qubits only get checked by one of these stabilizers. So error propagation. Even with surface codes, errors don't always stay in one place, and they can spread from one qubit to another as qubits interact. To track and correct this, we use something called stabilizer operations. These tell us where an error started and where it ended, but it does not tell us the path it took in between. And in quantum computing, there's no one predefined path. It can take multiple different paths. And The challenge is to like figure out that path. It's like the heart of like error propagation analysis.
All right, so as for a solution, like our solution is to replicate the surface code and use an MWPM, CNN, and GNN pipeline to find and fix these like error propagations, as mentioned previously, as fast and as reliably as possible. Yeah, so currently, as for what we've done so far, we use the QSurface Python module to replicate the surface codes and visualize them, which will make it easier for us to develop our models. So we made the CNN model powered by ResNet to pre-process the data and extract the features, which are the patterns that we're looking for in CNN, pretty much. And then we've currently formatted the CNN outputs so they're ready for the next part of our solution, which is the GNN, which actually like makes the predictions on where like on what the initial values were like based on like the errors. And like those two components are really important for finding and fixing errors in the surface code. All right. So this is an example of like how a Q surface would look like. So first, like this is with the MWPM decoder, that's by default. So like we have the initial like state, which like is like empty. So you can see like the big circles here are like the data qubits and like the small like squares like pointing to each of those circles are the ancilla qubits or like the stabilizers like as mentioned previously. So yeah, just go to next. Yeah, so like when we apply errors like with the thing that we have, like like the like colors will change pretty much and that like allows it to be like easier to visualize. So let's go to the next one. And then the ancilla qubits, like those will basically like light up like when we're doing testing, which like you can see like with around the like qubits that were like altered. And and then yeah, the matchings are when it like detects when it finally detects the errored qubits. And then yeah, that's just like how it would look like when decoded.
Okay, our results so far. So we extracted features from our CNN and used it for our GNN. We also used an image processor to make the surface code image. As you can see, we're using a 5x5 surface code. So like we also have like the output. So a node is just like a fancy term for like each of those like vertices. And tensor is just like a type of data structure. And in our case, that's just our data structure is gonna be the grid, which holds all the data. Future plans. So we plan on eventually transitioning to Qiskit for surface code visualization, since we can emulate quantum computers with it. We plan on retrieving the established MWPM decoder's accuracy to determine the baseline for our own solution. We will also develop the GNN, which makes predictions based on the features output from the CNN. And we also are looking into other research so we can improve our own and find what methods are better.
So this is our timeline. So we created information on like the surface code and we simulated the surface code with like noise model and created like a new set of data. We are also going to develop GNN and CNN models and we trained them with simulated surface code and like we evaluated the model's performance. So we'd like to acknowledge and give many thanks to Dr. McMahon and ASDRP and credit for inspiration that was taken from previous work done on similar topic by Pranal Gupta, Rohan Beg, and Dia Watsavi.
If you have any questions about a project at all, feel free to ask.